Now that we've talked about the general idea of what linear approximation really means, at least graphically, let's get an actual formula for how this might work for all nonlinear functions. Okay, let's again kill all the birds with one stone. To do that, let's think again about the general idea of the line. Remember, we're approximating any function by the equation of its tangent line at one particular x value, right? And remember that, in fact, the equation of a line, okay, the line we're looking for is going to be just y minus y1 is equal to m times x minus x1, right? This is just the general equation of a line. But we know in particular for any given function that the equation of the tangent line is given by, well, we know that the derivative of the function at some x value gives me the slope of the function of the tangent line, that is, at that x value, right? So in fact, this is equal to m. Okay, so that's what my m is going to be in this case. And then I'm going to have some point on the line. Okay, so my x1 and my y1 is going to be my point on the line. So that point, we know always, remember that every tangent line touches the function at one point. And that point is going to be, let me write it down this way. My x1 is going to be the x1 that we're given. Okay, and my y1 is going to be f at x1, right? That's how you write it down. So in fact, these are going to be my 2 points that I have. This is going to be my slope, and I'm going to be able to approximate anyway the actual function close by x, my given x value, by a line. Okay, the line of the tangent, okay, at that point specifically. Okay, so let's write this down in a better notation. Okay, so in particular, recall that the derivative of a general old function, doesn't matter what it is, in one variable, the derivative is going to be equal to, this is by definition the limit as delta x goes to 0, or delta x is also h, remember, it's that distance we're going. And it's going to be this limit of this difference quotient. It's going to be f of x plus delta x, that's where I'm going, minus where I came from, f of x, over the distance I've traveled, right? So it's sort of like change in y over change in x. Okay, and I can still rewrite this as the limit as delta x goes to 0 of delta y over delta x. Okay, this is really a slope, remember. And when I've taken the limit, after I've taken the limit, and only after I've taken the limit, these deltas go away and they become the little d's, dy, dx. Okay, that's when I've taken the limit. And that's the derivative. This is my Leibniz notation of the derivative, and we know this already. However, think of it this way. Remember that if we make some kind of approximation, right? So if we make delta x small enough, right? We're not taking the limit, we're just making it small enough. Then we could at least get some kind of approximation for the derivative. Okay? So that's what we're going to do. And that's what we're doing here, is we're actually approximating the value of the function nearby some x value. So in other words, if my delta x is small enough, right, it's close by my actual x value, I haven't gone very far, then I can use that to approximate the actual function. Okay? So let's just write this down. You'll see where I'm going in a minute. So if I remove the limit sign, in fact, what happens is I have to write down this little approximation symbol, okay, because it's not exact anymore. So f's derivative is approximately this for small enough x. Small, I should say, delta x, right? So for a small distance away from my value that I wanted, my x value, this is going to be a pretty decent approximation. And the smaller the delta x is, the better approximation it's going to be. Okay? And that's the idea of the limit, right? The limiting value. As delta x gets very, very small, I get closer and closer and closer to this being an equal sign. Okay? But if I remove the limit sign, I just throw the approximation on there. Okay? Now remember, I'm just going to rewrite this in a different way. All I'm going to do is I'm going to multiply both sides. This is an equation. I'm going to multiply both sides by delta x. Okay, when I do that, I get delta x f's derivative at x, okay, is approximately where the function's gone, right? So it's x, f of x plus delta x minus f at x, okay? And what I really want now is I want some kind of, well, line, right? I'm after this is what I'm after, okay? And in fact, this is exactly it. That is, think about it for a minute. The x minus delta x is really x minus x1 anyway. This is really a delta x, right? It's a distance I've traveled in x. So I can sort of think of this as a delta x. I can think of this similarly as a delta y, right? So this is like a delta y. And the m is really the f's derivative at some particular x value, okay? So this is really like f's derivative at x. Okay? And that's exactly what I'm doing here, is I'm just going to do the same thing and approximate with a linear equation. Okay? So I've got this already. This is my y minus y1. And this is my m times delta x. Okay, I'm going to rewrite it so in this same kind of form here. So this is the approximation. Okay? So the approximation is we have that f of x plus delta x minus f at x is approximately f's derivative at x times delta x. But there's nothing new about this. This is really the equation of this line up here. Right? This is the equation of the tangent line, okay, of the function f at the point x. Right? I've just written it in a more general form. That's it. Okay? We can, again, recognize this as really delta y right here. And why don't I just write it this way? Just say that really this is like my my y minus y1 is approximately, this is your m times x minus x1, right? Because again, my x1, y1 is the point that I'm at. I'm at that point, right? The tangent line touches the function f at the point x1, y1, right? And I can use this idea to get a linear approximation, right? Approximate the function a little bit away, slightly away, some slight x distance away from the x that I'm at, right? In other words, here's x plus a little bit more. So f at x plus a little bit more can be rearranged. I can rearrange this to get some expression for f of x plus a little bit more. That's what I'm trying to get at. Okay? Let me rewrite this so it looks a little bit nicer. Okay? Again, recognize that this is really the equation of a line that I've got up here already. Okay? But if I rewrite this a little bit, I can say that f of x plus delta x is really approximately f at x plus f's derivative at x delta x. Okay, notice that all I did in going from this step to this step is I simply took this equation and I added f of x to both sides. That's it. Okay? And this is the result that I have in the end. That in fact, f of my point x plus a little bit more, okay, can be approximated by f at x plus f's derivative at x delta x. This is the equation of a line. That's it. In fact, I can think of this as my y, right? This is really y is approximately y1 plus m times x minus x1. And if you rearrange this again, if I multiply these things out, this is the same thing as saying y is approximately m times x, right, minus mx1 plus y1. And what we have here is y is mx plus b. Okay, this is my b. My b is all this business down here. Okay? So this is just y equals mx plus b is all it is. That's all I've done. It's the equation of a line. But really what it's doing is it's approximating the value of the function just a little bit away from x. Okay? This is the general formula that I have. And if you can remember this, then it doesn't matter what f is. It can be any nonlinear function, no matter what it is. Even if I don't tell you explicitly what the nonlinear function is, you can still use this to approximate the value of this f at some x values nearby x. Okay? And it is extremely useful idea, the idea of a linearization of some kind of nonlinear function. Because again, some functions that are nonlinear are hard to deal with. And they can be very difficult to actually model. And so if we can somehow make them linear, they're a lot easier to deal with. And we can actually get exact values out in a much easier way. Okay, so this is the idea of linear approximation. And now that I have figured out how this works, let me rewrite this so it looks even nicer. That is that I'm approximating my value of my function f nearby. So let me write it this way. So we can approximate f at x plus a little bit, x plus delta x, by the equation f of x plus delta x is approximately f at x, just as I had written before, plus it's going to be f's derivative at x times delta x. And again, keep this equation in your mind where, again, my y1 is f of x. My m is going to be f's derivative at x. And my delta x is equal to x minus x1. Okay, so if you can think of it this way, it's just the equation of a line. That's it. Okay? And we're using the fact that if we zoom in close enough on any nonlinear function, then the actual function is really the same thing as the line, right? It's linear. But we're using the equation of the tangent line, that line, to approximate the function nearby the point where it touches the function. Okay? So in fact, so approximate near the point x and f at x, right? Nearby that point, any point nearby, if delta x is small enough, we can approximate in a linear way. We can linearize any nonlinear function.